Hey there, physics explorers. Let's start with something fun and relatable. Have you ever tried pushing a shopping cart with a wobbly wheel? As you start pushing, the force you need to apply might change, right? At first, it might be easy, but the more you push, the more resistance you feel. That's what we call a variable force, a force that changes as you apply it. In the real world, most forces we deal with are not constant. For example, when you push a spring, the force the spring applies back increases as you stretch it. So, just like the cart, the force changes based on how far it's stretched. In physics, when we calculate work done by a variable force, we can't just multiply force by distance like we would with a constant force. Instead, we have to use integration, a mathematical tool that helps us add up tiny amounts of work done over small distances. Sounds tricky? Don't worry, I'll break it down for you step by step. Let's dive deeper. When a force is variable, the total work done depends on how the force changes over the distance. Imagine you're pushing a cart, but the force you apply isn't constant. Sometimes it's stronger, sometimes weaker, depending on your effort or the resistance. The general equation for work done by a variable force is work equals the integral of force with respect to displacement, W equals the integral of f of x with respect to x. This just means, instead of multiplying force by distance, we add up all the tiny amounts of work done at each step. We are looking at the force changing as we move, and we calculate the total work done by adding up all those little bits. Think of it like summing tiny pieces of a puzzle. Each small piece of work comes together to form the total work done. So, for a variable force, we don't just plug numbers into a simple formula, we use integration to get the total work done. Let's make this a bit more concrete. What if the force varies in a simple, predictable way, like a spring that stretches in a straight line? When the force increases or decreases gradually over a given distance, we call it a linearly varying force. A great example of this is Hooke's law for springs, where the force is directly proportional to how much the spring stretches. Now, the work done by a linearly varying force is much simpler to calculate. Here's the formula. Work equals initial force multiplied by displacement plus half of the displacement multiplied by the sum of initial and final forces. W equals F sub 1 times D plus 1 half times F sub 1 plus F sub 2 times D, where F sub 1 is the initial force, F sub 2 is the final force, D is the displacement. What does this mean? Well, when the force increases or decreases in a straight line, we can imagine it as a rectangle, initial force times displacement, plus a triangle, the change in force over the displacement. The total work done is just the sum of these two areas. This formula is a great tool when dealing with forces that change steadily, like a spring being stretched or compressed. Alright, let's turn things up a notch. What happens if the force doesn't change in a straight line? Maybe the force increases rapidly or nonlinearly as the displacement increases, kind of like the force needed to stretch a rubber band. As you stretch it more and more, the force increases faster. In these cases, we need to use calculus to figure out the total work done. For a nonlinear force, the force can be described by a mathematical function such as force equals k times x squared, where k is a constant and x is the displacement. To calculate the total work done, we use work equals the integral of force with respect to displacement, W equals the integral of k times x squared dx. This means we need to add up all the little bits of work done as the force changes with displacement. It's a bit more complex than a straight line, but don't worry, the math is just about adding up tiny pieces of work at each point along the way. Let's bring everything we've learned into the real world. variable forces are everywhere in our daily lives. Here are some common examples. Friction. The force of friction isn't constant. It increases with the speed of the object. When you push a box on a rough surface, the force of friction is small at first but increases as the box moves faster. Springs. A spring has a force that varies depending on how much it is stretched. Hooke's law tells us that the force exerted by the spring is proportional to its displacement. A resistance. The force acting on a moving object through the air, like a falling parachute, increases with speed and slows the object down. In all these cases, the force changes over time or distance, and we need to account for that in order to calculate the total work done. Understanding how these forces behave is key to predicting motion in the real world. Let's look at a more detailed example. Imagine you're pushing a box. The force you apply starts at 100 newtons and gradually decreases to 50 newtons over a distance of 10 meters. What is the total work done? We can use the formula for a linearly varying force. Work equals initial force times displacement plus 1/2 times the sum of the initial and final forces multiplied by displacement. W equals F sub 1 times D plus 1/2 times F sub 1 plus F sub 2 times D. So, substituting the values, W equals 100 newtons times 10 meters plus 1/2 times 100 newtons plus 50 newtons times 10 meters. Simplifying, W equals 1000 joules plus 750 joules, which equals 1750 joules. So, the total work done is 1750 joules. Notice how the work increases due to the gradual decrease in force. It's a perfect example of how variable forces are different from constant forces. Let's wrap things up. Today we learn about variable forces, forces that change as they act over a distance. We saw that for constant forces, calculating work is easy. But when the force changes, we need to use integration or simple formulas depending on how the force changes. For linearly varying forces, we used a simple formula, and for more complex forces, like those that follow a nonlinear pattern, we used integration. We also discussed real-world examples like friction, springs, and air resistance, all of which are variable forces. Understanding variable forces is crucial for studying how things move in the real world. Whether you're dealing with a spring or a sliding box, work done by variable forces is a concept that's everywhere. I hope this explanation helped you understand how to handle work done by variable forces. See you next time with another exciting physics concept.